recording. All right, so we spent a lot of time looking at more differential equations, but in particular, looking at the type that are second order. And so the idea of second order differential equations in a variety of forms. So some of them are homogeneous, some of them are not. Some of them have constant coefficients and some have non-constant coefficients. So we've got non-constant coefficients, we've got constant coefficients, and everything that we've been working with has been second order. And it's been a lot of strategy, a lot of how do we know what method to use when. And so that is something that would be really important to think about as we begin to move closer to exam 2. All right, so thinking about how do we know what strategies to use would be super valuable. And I did already grade the homework 4. So if you have any questions about that, take a look at the answer key. So solutions are always posted for the homework assignments, but take a look at that. I know that some of us chose to do different methods for different problems than maybe what I had on the solutions. There are a variety of methods, as you'll learn. And as long as we're getting to sort of that same answer, it's typically fine which one you choose. And so keep that in mind. If you chose a different strategy, but it still worked out to be the same answer, you're good to go. All right. So what is new for this section? All right, we're going to revisit this idea very similar to 3.1. Why does any of what we learned matter? Why do we need to know all of these different strategies? And so the applications, I think, are the most important or the most exciting part about differential equations, right? We spend so much time doing all of these skills, but then at the end of the day, how does this apply? And the really neat thing is it applies to a bunch of different situations that we model in the real world. And so our focus for this section in particular is going to be looking at spring mass systems. All right, so we're going to be looking at spring mass systems. In other words, we have some sort of weight. It is attached to a spring. And how does that weight move over time, depending on sort of how stretchy or not stretchy the spring is, how heavy the mass is. Also thinking about, do we just let it go from rest, or are we starting it with some sort of motion? And so what we're going to do is we're going to take a look at 3 different categories of motion when we talk about spring mass systems, all right? And so the first category we're going to be looking at is something called free undamped motion. And then the second category, and I'll just kind of scroll through so we can see like the 3 main categories. There's free undamped motion. There is free damped motion. And then the last category, where is it? Is something called driven or forced motion. All right. So as we do the different problems, you're really thinking which one of these 3 categories is the situation in. Okay, so we'll still be practicing that idea of making decisions, but it'll be more situational, and we'll be able to tell from the equation as well what it is that we're trying to find. All right, so we're going to start with this free undamped motion. And some of you might have actually heard of this as something called simple harmonic motion. Anybody ever heard of simple harmonic motion? Well, simple harmonic motion is basically a situation where we're almost pretending like there's no friction, there's no air resistance, which is a type of friction, but it's almost like a system in a bubble. There's nothing really impacting that except for the spring and the mass. And so we're going to do a little bit of a derivation, but mostly talk through that concept. And then we'll really be able to practice, like, how do we unpack from the question what kind of motion there's going to be? And so you might recall from somewhere along your academic history that someone along the way said that force is actually equivalent to mass times acceleration. And in relation to springs, all right, we modify this idea of force to be force equals Ks. And it would be important to note here that K represents the spring constant. And what I mean by spring constant is like, how stretchy is that spring? So is it really easy to stretch? Is it not so easy to stretch? That would be a K value. And then the S represents the distance that the spring is stretched. All right, so we have this spring, we are stretching it. How far we are stretching it is modeled by the letter S. Now, when we have free motion, all right, this idea of free motion, that means that there's nothing outside of the spring and the mass that impact the motion of the mass, right? It's literally like you took it and put it in a bubble. And so we're going to consider the following differential equation, all right? So we have this differential equation right here, all right? M d squared x dt squared equals negative kx. And if we were to think about using some algebraic manipulation, all right, and in particular, if we took this equation and we did two things, we divide by m and we move all terms to one side. All right, so if we divide by m and we move all the terms to one side, we get a different variation of this formula. All right, so we still have the second derivative of x plus omega squared x equals 0. And so I do want to point out that this right here, right, this is not a w, this is omega. And we use this a lot when we're looking at sort of vibrations or spring mass systems, okay? And so you might be wondering, where did this omega come from? Because we didn't even see it in the other equation. And so if we sort of take this step by step, all right, we divide through, we're going to get d squared x dt squared plus k over m x equals 0. Right, so if we divide by m and we move all the terms to one side, we're going to get an equation that looks something like this. Now, one of the things that folks who are in the world of differential equations really love is making their lives a little bit easier with the notation. And so it turns out that they've said that omega squared is equivalent to this fraction, k over m, right? So omega squared is equal to k over m. And where do we find that k over m? Well, k is just our spring constant, and m is going to be the mass of the object, all right, whatever it is that we're attaching to this spring. And so a lot of times you might see a different letter in that final equation. It would be really important to make sure you know where that letter came from, right? What is a different way of writing that letter, all right? And so we have this differential equation. We look at it, it is indeed homogeneous, right? We have the second order differential equation, it equals 0, so we know that it's homogeneous. And so I'm wondering if we just had this d squared x dt squared plus omega squared x equals 0, what technique would you say that we should use to solve this based off of what we learned in the last week or two? Are there any techniques that are coming to mind? All right, I see something in the chat about a linear. And so if we're looking at this, it would be valuable to know we have a second order situation. And one of the first techniques that we learned about with this second order differential equations is what happens when we have constant coefficients. Okay, and so when we look at this, it might be important to notice that we do indeed have constant coefficients. All right, now constant in the sense that the coefficient in front of that second derivative is a 1, and the coefficient in front of the x is omega squared, which comes from k divided by m. So that's going to be a number, all right? So when we've got constant coefficients, what we really want to be thinking is, how can we use that characteristic or auxiliary equation to solve? All right, and so in this case, I'm wondering if you can tell me, based off of this differential equation, what is the characteristic equation that goes with this differential equation?
Is it r squared plus 1?
Yeah. We could say that we have, if you want to use the letter R, that is absolutely fine. So maybe I say, whoop, A equals 1, B equals 0. But hang on one second, what does C equal? C is just the coefficient of our x, so it is indeed omega squared. All right, it is omega squared, it's not a 1. We actually want to grab this as the number that is that coefficient. All right, and so if we take these coefficients and we plug them into our characteristic equation, we can say that we have 1r squared plus 0r plus omega squared equals 0. And in fact, we can take that to say r squared plus omega squared equals 0. All right. Now, if I want to solve for the root, I can go ahead and subtract the omega squared to both sides and then go ahead and take a square root, right? So I'll have r squared equals negative omega squared. R equals plus or minus the square root of negative omega squared. All right, and we can actually take that and say, when we take the square root of a negative, we're going to have an I, and the square root of omega squared is just omega. All right, and so even just by writing out a little bit of this solving in a generic case where we don't know a number for omega squared, but we know it's a number, we can see why people who do this kind of problem a lot might choose an omega squared to replace k over m. Because all it does is at the end, they just have a nicer number. It's a square, so when they take the square root, you'll just have the original omega. Okay. Now this would be the same thing as saying plus or minus the square root of k over m times I. Right? They're not different from each other, but it is, I would say, in purely out of convenience that folks choose the one on the left-hand side so that they don't have to write a square root symbol and a fraction underneath there. Okay. Now, I have at the end found that I have complex roots. And so if I have complex roots, what is the general form of the solution? What do we have as the general form of the solution here? Is it going to have e's in it? Is it going to have x's in it? What's it going to have in it?
It's going to end up coming out to just C1 cos omega x plus C2 sine omega x.
Exactly, exactly. So we're going to have our one with the cosine and the sine. And I do want to actually point out something. So the general form as we have it, it has an e in it, right? It's actually C1 e to the alpha cosine of beta x plus C2 e to the alpha sine beta x. And so one thing that I've noticed on a few papers, not a whole lot, is that some folks are not sure what to put for the alpha. And so they still end up with an e to the something term. But if we write it out as 0 plus or minus omega I think that makes it a little bit easier to see. We're going to plug in 0 for alpha. And so e to the 0 is just going to go to 1. And the same thing over here, e to the 0 is going to go to 1. And that's why we're only left with the sine and the cosine terms in here. Okay. And so in this particular case, we have x of t equals C1 cosine omega x plus C2 sine omega x. All right. So in general, that's going to be the form of the solution that we're looking for here. Okay. So we've got this differential equation. We've manipulated it and rewritten some terms to make it easier for ourselves. And that was like I'm asking you to trust me on that situation. But once we've used the characteristic equation, I think it becomes a little bit more obvious why we would choose an omega squared instead of the keeping it as the k over m. And then this last piece here, I just want to make sure if that was a mistake you made, you ended up with a lot of extra terms in that homework number 4. Remember, if it's just a plus or minus something I, that means that the alpha or that first part is actually 0. And so that means that you won't have any e to the power of anything in your final general solution. Okay. And so this is sort of like a big picture overview, but let's see what it looks like in the context of an actual problem. Okay. So let's take a look at this example right here. So we have a mass weighing 2 pounds and it stretches a spring 6 inches. At t equals 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity of 4/3 feet per second. Determine the equation of motion. And so as we approach these kinds of questions, I like to think about it in terms of just like if it were a regular differential equation without the context. And so we're going to have to write this differential equation, meaning we're going to have to figure out what this looks like. That second derivative plus omega squared x equals 0. Let's find out what our omega is, because once we have the omega, we'll be able to write that differential equation. And once we write the differential equation, we'll be able to use all the stuff we learned in chapter 4 to solve that differential equation and obtain a general solution. And so these kinds of questions, before we jump right into that, we always want to make sure that we do a little bit of what I call pre-work or pre-thinking. because we might need to convert some units. Okay, we might need to convert some units. And that depends on the particular situation. But typically when we have like feet and inches, anything in this imperial system that nobody else in the world uses except for us, we are going to be converting some units. Okay. And so what we're going to start off with is we're going to start off with the 2 pounds, and we're going to think about how we can take the pounds and turn it into an actual mass. Okay. So we have 2 pounds. What does this 2 pounds stand for? 2 pounds is the weight of the mass. All right, 2 pounds is the weight of the mass.
Sometimes it just doesn't work. No? Oh, I hope not.
All right, so 2 pounds is the weight of the mass that we have here. But when we look at the equations, in order to have our omega, we need to know omega squared equals k over m. Oh, you're fine, it happens. So we need to find our k in order to write the omega squared, and we need to find the m in order to write the omega squared. And so what we're going to do first is we're going to find the m, and the m is something we can find from the weight. Okay, so we said earlier that force equals mass times acceleration. And another equivalent way of saying that is that the weight is equal to the mass times gravity. All right, the weight equals the mass times gravity. And so when we think about that, this 2 pounds that they've given us is the weight. And we know what gravity is. We can plug that in for gravity, and that's going to allow us to find the mass. Okay, and so we can maybe say here that mass is going to equal the weight divided by gravity. And the weight that they've given us is 2 pounds. And gravity, which we're going to use, and I think I've given this to you in homework 5, is 32 feet per second squared. Okay. So we'll have 2 pounds over 32 feet per second squared. That's going to give us a mass of 1/16. And the units that go with that, I don't know, I should actually look up how they came up with this name, but it is 1/16 of a slug. Okay. My guess is it does not have to do with the actual animal, but I couldn't tell you for sure. I know, it's kind of delightful. If you're ever feeling like you want to nerd out a little bit, I would look up the names to all of the special particles in quantum physics. They have some really cute names, and the story behind them is actually pretty cute. All right, so we found our mass, which is great because that is half of what we need to find our omega squared. The other thing we should do is we want to notice that when we talk about gravity, especially in the imperial system, we're measuring things in terms of feet, but in the question, they've given us things in terms of inches. And so we're going to go ahead and convert those as well. Okay, and so we're going to take, let me put a little bullet point here, 2 pounds, 6 inches. If I were to convert that to feet, would give us a half a foot. And if we were to take the other distance, 8 inches, and convert that to feet, that would be 8/12, or 2/3 of a foot. All right, so I like to do that before I get started, which is basically just make sure that all of my units are in the right type of unit so that when I start plugging numbers and things, I have a little bit clearer idea that I can just take those numbers and plug them in, because otherwise you'll end up with some weird sort of answers. All right, so after we convert our units, I find it very helpful, because now we found our mass, I find it very helpful to find my K. Because once I have my K, then I can say this is my omega squared, I can use the characteristic equation, and all will be well with the world. All right, so if we're finding K, we're actually going to go back and grab an equation from above, which is this force equation. We're going to say that force equals K times S. All right, so the force will equal the spring constant times the distance that the spring is stretched. And if we take that and say F equals KS, and we plug in some numbers, well, what is the force? The force is actually the weight of the mass, okay? So the force is actually the weight of the mass. And so I'm gonna go ahead and put 2 pounds in for the force. Now, K, I don't know because I'm trying to find that, but how long of an extension, like how much did the length of the spring change once we put this weight on the spring? Well, they tell us that in that first sentence, right? They say a mass weighing 2 pounds, as soon as we hook that onto the spring, it stretches the spring by 6 inches. So that distance is going to go in for our S, but we don't want it as 6. We want to use 1/2 so we can keep it in terms of feet and pounds. Well, that means that K is going to equal 4. All right, so we found our K, we found our M. That means now we can find our omega squared. All right. All right, so let's solve this. Let's write our differential equation, then let's solve it. All right, so if we were to write and solve, we're saying we want to use the general form we saw above. So d squared x dt squared plus omega squared x equals 0. And now we just need to plug in our omega squared, okay? And so from here, we can see that we'll write it as d squared x dt squared plus, let's see, omega squared is just K divided by M. So I'm going to take 4 and I'm going to divide it by 1/16. All right, so 4 over 1/16 x equals 0. Now, if we simplify that, we'll get that second derivative plus, let's see, 4 times 16 gives us 64. And so this is actually the differential equation that we want to solve, okay? So I'm going to have you go ahead and solve that differential equation. So write the characteristic equation, solve that, and write the general solution. I'll give you a couple minutes to do that, and then I'll write my version up here. And we'll make sure that we match. Of course. There we go. All right. So if we were going to write the characteristic equation that goes with that, we might say r squared plus 64 equals 0. And then we can solve for r by saying r squared equals negative 64. That's going to give us roots of plus or minus 8i. Okay, plus or minus 8i. Now, I am going to take a moment and write it as r equals 0 plus or minus 8i. Okay, just as that reminder that there shouldn't be any e terms in there because we're saying e to the power of 0, which goes to 1. Okay.
Hey, Judy,
Yes, go
I
ahead.
think I'm missing something here, but isn't it omega squared?
It is, but it's not. Omega squared is equivalent to k over m.
Oh, I see. Okay, thank you.
Yeah, this is a pretty common theme in a lot of the differential equations. We'll say, I know at some point I'm going to take a square root. So I'm just going to call it something squared so that when I take the square root, I'll have a nice number to plug into the answer. All right, but super good question. So we've got these roots, 0 plus or minus 8i. That means that our general solution is going to be x of t equals. Now, if we were to write out the whole general form, c1 e to the alpha cosine of beta t plus c2 e to the alpha sine of beta t. If we go ahead and plug in a 0 everywhere we see the alpha, and everywhere we see a beta, we're going to plug in that 8. That will give us c1 e to the 0 cosine 8t plus c2 e to the 0 sine of 8t. And so this is where, why aren't there e's in the answer? Because both of those e to the 0s, they go to 1, okay? And so that's why we suddenly get a solution that does not have the e's in it. All right, are there any questions about the general solution here? Because we still have a little bit to go with this problem. So let me put this on one page so we can sort of see our conversion, our finding our k value or the spring constant, and then writing and solving that differential equation. All right. So the last part, you might be wondering, what else do we have to do in this problem? Well, in this question, there are secretly buried some initial conditions. Okay. Now, how would you know that? At t equals 0. Okay, at t equals 0. That tells us that they're saying at the initial time, we know something about position and we know something about velocity. And what that's going to allow us to do is actually find values for our C1 and our C2. Okay. So there's a lot of interpreting in these kinds of questions. Like we want to see the question for what it is, but we need to do some conversions. We need to find some values so that we can create and solve this differential equation. And so how much space did I leave myself? Ooh, mostly enough. So we're going to use the initial conditions to find the equation of motion. And so maybe it would be beneficial to write down what our initial conditions are based on what we have from the question. And so if we go back up here, I notice that at t=0, the mass is released from a point 8 inches below the equilibrium position. And so what I can say is that one of my initial conditions is x of 0. So x being like position. So the position at time 0 is actually 2/3. So we're using 2/3 because that is the foot equivalent of 8 inches. All right. Anybody wondering why that's not negative? Might seem like it should be negative, right? Because we've got below the equilibrium position. And so the reason why it's actually not negative is because we're saying whatever the direction is with gravity, that's going to be sort of our positive direction. Okay, so maybe we make a note of this, that the direction with gravity is positive. Okay. Now, other textbooks or other instructors might do that differently. And so I just want to point this out, that it's all about the relationship between things. So if you define one direction as positive, that means that your other direction will be negative, and that you just need to compensate for that as you move through the problem. Okay, so I'm basing this off of the idea that everything in the same direction as gravity is positive, which means everything in the downward direction is positive. And so I can say that the position at time 0 is 2/3. But if I wanted to say velocity, well, velocity is actually the derivative of position, right? X prime of 0. That means the velocity at 0 is going to be 4/3. And I'm leaving this aggressive space between the equals and the 4/3 because remember, everything for me with gravity is positive. So if you're moving upward, that is against gravity, I would actually call this a negative 4/3. All right, so this part right here is probably pretty important. And the most important part about that is that it makes that it all fits together, right? If you designate one direction as positive, then the opposite direction of that must be negative, all right? Where did we get the initial gravity, like the 32? Good question. So it's one of those sort of nice values to know, so to speak. All right, where it came from, the need for it is because we said we wanted to find mass, and mass is weight divided by gravity. And so we knew the weight of our object was 2 pounds, but in order to find the mass of it, we needed to divide by gravity to find the mass. All right, so it really comes from this equation right here saying, I have the weight and I have gravity. I want to find out mass. All right, but it was not given to us in the problem. I think in the homework, I did write like use 32 feet per second squared for gravity. Okay.
Hey, Judy, are we ever in this class, are we doing anything in standard units, or is it all going to be empirical?
No, it'll be some standard ones as well. I think I tried to mix it up on the homework. All right, so let's grab these initial conditions. We're going to bring them back down below and we're going to apply those initial conditions. Well, that's not what I want to do. All right, so as we've seen before, if we want to use the initial conditions, one of them we're going to be able to plug right into our equation of motion, but the other one, we're going to have to take a derivative of this general solution so that we can use that second initial condition. Okay. And so if we plug in the first initial condition, I'll get 2/3 equals C1 cosine 0 plus C2 sine 0. And what I can see from here is that knowing my unit circle value is super, super helpful because sine of 0 goes to 0. So that whole second term goes to 0, but cosine of 0 goes to 1. And so we're able to see from this first initial condition that C sub 1, our first constant, is equal to 2/3. Now we just have to take the derivative of this, plug in the second set of initial conditions and find C2. So we're going to get x prime of t equals, let's see, chain rule. So negative 8c1 sine of 8t plus chain rule again, 8c2 cosine of 8t. All right, we're going to plug in 0 everywhere we see a t, and the left-hand side will become negative 4/3. So I get negative 8c1 sine of 0 plus 8c2 cosine of 0. Once again, I know that the whole first term is going to zero out because sine of 0 is 0. And cosine of 0 is 1, which gives me negative 4/3 equal to 8c sub 2. And if we divide by 8, we'll find that c sub 2 is equal to negative 1/6. Okay, negative 1/6. So we found our C1 and our C2. I know that this has taken up quite a bit of room. If you are someone who works on a tablet, you can take your work and sort of shrink it just a little bit to give yourself a little bit more room. So if I were just to like scooch this up a little bit, it'll give me just enough room on the bottom to write that final solution. All right, but you do want to make sure that you write out that final answer. All right, so most of us are doing that. A handful of us are still not writing that final answer, but please, please, please make sure at the end, you're going to take your x of t. Everywhere we see a C1, we're going to put in the value we found. Everywhere we see a C2, we'll put in the other value we found. So 2/3 cosine 8t minus 1/6 sine of 8t. Right, and so this is our equation of motion for this particular spring mass system. All right, so let me get that all on one page for you. It's a very solid page of work that we have right here. And let's take a moment and see if there are any questions before we get started on the next one. All right. Well, if there are no questions right now, maybe it would be helpful if we tried another one like this. It'll be sort of that same flow. We're going to convert the units. We're going to find K. We're going to write and solve the differential equations. And then we're going to use the initial conditions to find our equation of motion, meaning find the coefficients. Okay. So let's go ahead and take a look at this example number 2. All right. We do have something in imperial units again, and we can tell because we right off the bat, we have pounds, we have feet. All right. So a 16-pound object stretches a spring 8/9 of a foot by itself. There is no damping and no external forces acting on the system. the spring is initially displaced 6 inches upward from its equilibrium point and given an initial velocity of 1 foot per second downward. Find the displacement at any time t. All right, so find the displacement is another way of saying find that equation of motion. And so let's go ahead by converting, or start by converting any units that we might need to. It seems like this problem is a little bit nicer in that they didn't give us anything in inches really, except for that 6 inches here. A lot of it is already in feet. But we are going to take a look at the 16 pounds. All right, so 16 pounds. This is the weight of the mass. Okay, the weight of the mass. And from our previous problem, we know that weight equals mass times gravity. And so if we want to find m, which is going to be important because we want to find omega squared, right? So in order to find omega squared, we need m. And in order to find m, we're going to use the weight they gave us, divide by gravity, and that will give us our m for mass. Right, so we have 16 equals m times 32. That's going to give a mass of a half slug. Half slug. All right. We want to take our 6 inches. We're going to remind ourselves that is the same as a half a foot. And the 8/9 of a foot that is already in the question, we don't need to do anything to that because everything else is already in feet. All right, so it's mostly when you see pounds, you want to make sure that gets changed to slugs. If you see inches, then you are changing to feet. Right, now the beauty of this is this gives us our m. That's halfway to finding our omega squared. But in order to find omega squared, we also need our spring constant. Right, so that's where the second part comes into play. We're going to find K, also known as that spring constant. And to do that, we're going to say force equals the spring constant times the distance that it was stretched. All right. And it is very handy to know that this force is actually the weight of whatever object you hook onto the spring. All right, so our force in this case is 16. I don't know what my spring constant is, but as soon as I hook that 16-pound object onto the spring, it got the spring to be 8/9 of a foot longer. And so that's why I can put in S as 8/9. I'll do a little bit of algebra. I get K equals 16 times 9/8, right? If I multiply by the reciprocal on both sides, and we'll do a little mental math, and we should get that K, in this case, equals 18. Right? So all of this pre-work is to say, I know in order to write my differential equation and solve it, I need to have omega squared. I need K. I need to divide that by m, and then I will get my omega squared. So in step 3, we are going to write and solve the differential equation. All right, so write and solve the differential equation. And so our general form, we'll just write that up here. D squared x dt squared plus omega squared x equals 0. And maybe noting that omega squared is K over m. All right. I know it's kind of weird, like, why wouldn't I just write K over M in the equation? Like, why am I making you remember separately that it comes from something else? The best answer I can give you on that is it's just convention. As you'll see, if you take other differential equations classes, it's just easier to have the general form as like something squared, okay? So if we plug in what we have, instead of omega squared, I'm going to take my K value, which is 18. I'm going to divide it by my M value, which is 1/2. So I have 18 divided by 1/2. If I calculate that out, I'll get 18 times 2, which is 36, x equals 0. All right, let's write that characteristic equation. We'll get r squared plus 36 equals 0, or r equals 0 plus or minus 6i. Right? We subtract the 36, we get a negative 36. So we know when we take that square root of a negative number, we'll have an I component to it. Now, again, I won't write it out this time, but this 0 in the front is a reminder for us. Okay, it is more a reminder than anything else. It is a reminder that we're not going to have any e terms. We're only going to have sines and cosines in our general solution. And in fact, we can say that x of t will equal c1 cosine 6t plus c2 sine of 6t. That is our general solution. But if we want to find sort of the particular displacement for this system, that is code for, I want you to find C1 and I want you to find C2. All right, so if it is specific to a situation, we want to find the coefficients. All right. And so in the last step, we're going to apply initial condition and find equation for displacement. Right, all of that, again, being very fancy talk for, I need to find C1, I need to find C2. All right, let's go back up to the problem. Let's figure out what these cryptic initial conditions are, because they didn't say, here's my initial conditions, they sort of hid it in the words. And so I'll give you a moment to sort of look over the word problem. And as you are looking over that, I'm wondering if you can tell me, and just by maybe dropping it in the chat or unmuting yourself, what initial conditions are sort of hidden in this situation. All right, I see that the initial position, so x of 0 is going to be 6 inches. All right, now I see the -6, and because it's originally upwards of 6 inches, but up is against gravity, we're going to say that's a -6. Good, good. And then x prime of 0, right? So x prime meaning another way of saying velocity, x prime of 0. What is that initial velocity? Well, it is 1 foot per second, but in the same direction as gravity because it's going down. And so that 1 will be positive. So let's grab these initial conditions. Let's bring them back down here with us. All right. And now we're going to be able to plug in the position 1 right away into that general solution. But to plug in the second initial condition, we're going to have to take a derivative. All right. So if I use the first one, I'll get -6 equals C1 cosine 0 plus C2 sine 0.
Isn't it 6 inches? Shouldn't that be -1/2 foot?
It should 100% be a -1/2. Yep. Thank you. I was like, that does not look like what I have here. All right. We want to remember the work we did, right? We set out to change the units and convert them appropriately. So we want to use the units that we converted to. So we've got that -1/2 instead of the 6 inches. And our cosine of 0 will go to 1. And so right away, we're able to see that C sub 1 equals -1/2. Right. We're going to do a little bit of work. We're going to find that first derivative. We're going to need chain rule. So -6 C1 sine of 6t plus 6 C2 cosine of 6t. And now I'm going to go ahead and plug in the initial condition. So I get 1 equals -6 C1 sine 0 plus 6 C2 cosine 0. And this whole first term is going to go away. Cosine 0 goes to 1. And we will get C2 equals 1/6. All right. Last but not least, we want to write our equation for displacement, which means that we will write the same equation we had before, but just with the constants or the coefficients that we found. All right, so let me go ahead and zoom in so you can see this all on one page. All right, how we feeling about this second example? Any questions or concerns coming up? All right. So I think it is a valid question, maybe as you're thinking about what we just did, like, how did we know that these were a situation that is simple harmonic motion, or we said free undamped motion? And I think sometimes we don't know because we start with this sort of very ideal case. We don't know until we get to another situation where there's more information that we're like, oh, I don't know what to do with that information. Okay, so we're going to take a look at this next section, free motion. So it's still free motion, but there's damping involved here. Okay. Now, damping typically refers to this idea that we're considering more factors of what's happening in the system. That is, there might be some sort of air resistance, or resistance from the whatever the object is moving in. So you might have a spring and a mass in like really goopy slime or something that would impact the motion of the mass. And it would behave very differently than if you had it sort of out in the open air, or maybe even in water, right? Things move differently in different mediums. And so this free damped motion starts to take some of that into account. And so let's consider this differential equation. All right. And let's kind of think about, again, how we get from the one on the left to the one on the right. And we'll notice again that there's sort of some new letters that pop up on the one on the right. And like, where does that even come from? Okay. So it turns out that from this initial differential equation, all right, before we start moving things around, we have a new piece. And in particular, we have this negative beta dx dt. Now, it might be helpful to remember that dx dt, that talks about velocity. All right, so we're now introducing a new factor into this spring mass system where there might be something that impacts the velocity and how the velocity changes. All right, so now it's not just acceleration, but it's like acceleration and velocity are changing the position of whatever mass we have. And it turns out that if we follow these same two ideas, so we divide by m, and we move all terms to the left-hand side, right? If we just did that part, we would get d squared x dt squared plus beta over m dx dt plus k over m x equals 0. Right? So if all we did was divide over and move all those, or divide by m and move all those terms over, we would get something like this. And as we kind of saw in the previous question, it was a little bit easier for us to think about omega squared as a different way of writing k over m, but that those two were equivalent. Omega squared is equal to k over m. Similarly, if we take this beta over m and we replace it with this 2 lambda, it actually makes life a little bit easier on the back end, okay? I hate leaving sort of explanations like, I promise it'll make sense later, but this is a moment where I'm going to say, like, kind of trust me on this. I'm going to see if I can find some better examples of, like, you know, in other courses where you might see like where it's really necessary to rename these variables, but all of it comes down to a convenience factor. Okay, it's literally about convenience. But we have k over m is the same as omega squared. Beta over m is equivalent to something that we're going to call 2 lambda, okay? But let's talk a little bit about what beta is, because we didn't actually, we just introduced this new letter, but like, what does it stand for, okay? And so it turns out that beta is indeed our damping constant. Right? Meaning this is the factor that sort of impacts how the spring mass system is moving in whatever medium it's moving in, okay? Now, we're not going to solve this differential equation in the general form. I think this one is actually a little bit easier to do with specific numbers. But what I did want to say is that you will still have a situation where you have constant coefficients. All right, so this still gives us constant coefficients, which means that we're still going to use characteristic. We're still going to use our characteristic equation because we have constant coefficients and it's homogeneous. All right. Now, if it's factorable, excellent, definitely factor. right? But one of the reasons why we have it as a 2 lambda, and I won't go through the entire derivation of this, but it turns out that the roots, so root 1 and root 2, if I put all like my beta over m, k over m into this quadratic formula, what I'll end up with is my roots will be negative lambda plus or minus the square root of lambda squared minus omega squared. And so if you remember, the quadratic formula has like a divided by 2a on the bottom. This 2 in the 2 lambda helps get rid of a fraction situation when you find your roots. All right, so it is genuinely about convenience. That's why we call it a 2 lambda. All right, I think we have time to take a look at one example, maybe more, but whatever we don't finish today, we'll go ahead and finish tomorrow, okay? I think I've made you watch enough videos on your own time, and I'd like to make sure you feel supported in this last section before exam 2, okay? So let's take a look at this table before we move into that example, all right? So if we have a differential equation where we have some sort of damping constant situation, there are sort of 3 outcomes for this situation, okay? It turns out that we can have a case where that discriminant, that's a word from the past, that discriminant is greater than 0. That is actually really similar to our idea that we have real distinct roots, right? This right here means that their roots are real and distinct. Because even though you have to use the quadratic formula, at the end you get real numbers and they're different from each other. It turns out that if that is what happens, you have real distinct roots, you have something called an overdamped situation, okay? The best way I can think of to describe overdamped is that your spring mass system doesn't move very much. It's almost like if you put a spring mass system inside, I think I used the example earlier of like slime or like mud or something like that, very thick medium. If you put it in something that is really thick, it might move initially, but then it doesn't keep moving back and forth, right? It just sort of moves and then slows down pretty quickly. That is what I want us to imagine when we're thinking about an overdamped situation. Okay. On the other end of things, what happens when you get complex roots, as in case 3, right? What happens when that discriminant is gives you an imaginary component? That's what we consider an underdamped situation. Underdamped is very much the opposite of overdamped. Underdamped means that it's almost like simple harmonic motion, like your spring mass will continue to vibrate for a fairly long period of time. Okay, so there's not a lot of resistance going on. It's pretty able to move freely. And there's one sort of sweet spot in the middle where we might have real and repeated roots. And it turns out that that situation we call critically damped. Critically damped is, it's very much like the, like Goldilocks and the 3 Bears, like whatever the medium one was, like the porridge was just right. The bed was just right. That's sort of what we can imagine this critically damped as, meaning that it moves, but if we were to change that damping factor just by a little bit, it would allow the system to move a lot more and move into this realm of underdamped. Okay, so I think it's maybe easier is t included in those square roots? No, it is not. That's a great question. T is not. Okay. So if we zoom in here, maybe let's make this a nice bright yellow color. This t is not under the square root. And then again here, those t's are not under the square root. All right. So if you're sort of a visual thinker, you like to consider what's actually happening in a system, it's kind of neat to think about these three cases. Like before, like last week, we were like, there's real and distinct, real and repeated, complex roots, right? That we know that from all our days in algebra, that there's different kind of roots that we can have. But the fact that they correspond to different types of situations, like maybe a very slimy or muddy something that we're moving through, maybe something that has very little resistance to something sort of right in the middle, that's what those actually correspond to. And I think that's the cool part about differential equations. All right, so let's take a look at example 1 here, or 3, and let's see how far we can get, okay? So example 3 says that we have this situation. The first part of this should look very familiar, right? We've got a 16-pound object that stretches the spring 8/9 of a foot by itself. The spring is initially displaced 6 inches upward from the equilibrium point and given an initial velocity of 1 foot downwards. That was all that we saw in example 2. Here's the new information. A damper is attached so that it exerts a force of 17 pounds when the velocity is 2 feet per second. Right, so we've got some extra information here. We're going to set up the flow of this very, very similarly. We're going to convert. We're going to find out some values, and then we're going to use those values to write and solve our differential equation. Right, and we're going to finish things up by saying, what are these secret initial conditions in here? And how do we apply them to get a very specific equation for this system? But last time, we only needed to worry about finding omega, or in particular, omega squared. This time, we also need to find that 2 lambda. All right, so there's another piece of information that we're going to have to find. So let's start with our conversions and let's see what needs to change. We know from above that 16 pounds is the same as a half a slug. We know that 6 inches is the same as a half a foot. I'm going to write that down so I don't make the same mistake that I made earlier, right? So we have our 16 pounds as a half a slug, our 6 inches as a half a foot. And I think that's it in terms of things that we might need to find for right now, okay? We can always come back and add to that if we need. But before I said, I want us to find K. But now what we're going to do is we're going to find K and our 2 lambda. Okay, our K and our 2 lambda. And so to find our K, we're going to use that same equation before. F equals K times S. And we know that our weight of the mass is 16 pounds. And that stretches the spring 8/9 of a foot. And we found this earlier to be K would be 18. Now, how do we find our 2 lambda? So 2 lambda, we said earlier, is the same as this beta divided by m. All right, beta divided by m. Any thoughts on how we can find a beta or an m? Well, the m we have, right? Our m we have already. How do we find that beta? While we're thinking about that, let's kind of put it into context, like, why are we going to need this value, right? And we know from above that this general form looks something like this. That if we only had these values, we could write our differential equation, and then we could solve it using our characteristic equation. Okay. Now I will tell you this. My characteristic equation I'm going to be able to use these values. Right? So knowing that we're going to come back together tomorrow to talk about this, I'd like you to do a little bit of research tonight or after this class. How did I get that 2 lambda to be 17? Okay, I think that's a really important question to be able to answer, right? Where did that 17 come from, and how could I replicate that for a different problem? But in these last few moments, let's take a moment to find the roots of this characteristic equation, okay? So we have r squared plus 17r plus 32 equals 0. And this one is not factorable, which means we'll need to use the quadratic formula. And we'll get negative 17 plus or minus, let's see, 17 squared minus 4 times 32 times 1 over 2. And I think that gets us something like this. All right. Now, one thing that I will say is I saw some folks who who did the quadratic formula, and then just because it involved like a square root, there were some folks who put this in as a complex general solution. It's not complex though, right? Because it has real values. Like this 161 is a positive number. It's not a negative number. So it's okay for you to have sort of not a nice number in that root as in the power of E. That's okay. That is 100% okay. All right. So just be really careful. Like if your roots are real and distinct, you need to put them in that general form. Whereas if they're complex, you're going to put them in a totally different form. Okay. All right, so we found this. How do we put that into our general solution? Well, we'll have x of t. And this is where it would be really important to go back up to that table that we had from earlier and write down what those general forms are and where we put all of those specific numbers, okay? And so what I'm going to do for the sake of time right now is I'm going to go ahead and grab this equation. I'm going to place that right down here. right? And when we meet again tomorrow, what I would like you folks to do is to write out what that general solution might look like based off of what we have in this form. Okay, so you're going to go ahead, you're going to write that general solution. We'll check that over before we jump into the lecture of tomorrow. Okay, so write that general solution and figure out how we found that 2 lambda. All right, and we'll make sure that we're all feeling pretty clear on that tomorrow when we come back into class. All right, so we'll stop the lecture here for today. Tomorrow we will pick up with the second half of 5.1, and in particular looking at how do we know what the 2 lambda is and how do we write that general solution for this new case. All right, so I'm going to stop the recording right here.